Welcome to all of you. In this class, we will discuss here one important topic of the electronic devices and which is known as the field effect transistors. Field effect transistors. What is the basic behind the field effect transistors? All the transistors has been invented just to amplify the signals by some physical or the manual manipulation in the device. That means firstly the entire transistor theory is coming from the vacuum tubes. Then they have invented some new design of the architecture in the solids, and that is known as the solid state triode. But in the solid state triode they face the difficulty to fabricate that particular structure, whatever they are trying to discuss. Whatever they are trying to achieve, that particular combination is very difficult to fabricate in any particular device. That is why that idea failed for some time. Then the new device of the transistor came, that is known as the bipolar junction transistor, because the fabrication process is not that much sophisticated required for the BJT. But after some time, when the fabrication processes and the laboratories are becoming very proper and which can achieve the desired architecture for the FETs, then this particular FETs was become very popular in the electronic industries. Okay, the idea of the FETs was invented earlier, but because of so much sophisticated process required in this idea dropped for 40 years. The first idea of the FETs was invented in 1925, and it will go up to the rigorous practice to involve the processes by which they can achieve some desired specification of the device. And they have invested 40 years, and then 1965, they introduced this device in a different manner, and that is known as the FETs. That means the principle of the solid state triode and the principle of the FETs are quite similar. But the physical realization of the triode was not possible, that is why that idea was dropped there. And in 1965, again, the scientists worked for 40 years and they introduced new device with a little bit different architecture, and they are trying to achieve the same type of specification as the triode. And those type of devices are known as field effect transistor. What is the meaning of this? That means basically here whatever the conduction you are doing with the device, that is basically depending on the electric field. Okay, that is why it is known as the field effect transistor. That means whatever the conduction you are getting, that is just because of the applied field. And we will see how it will work. But firstly I want to characterize this particular FETs. FETs can be of two types. FET can be a JFET or junction field effect transistors, and the second one is MOSFETs. Now this MOSFET is a new very boom topic of the electronic devices and major area of the research at this time, because the packing density of this particular device is very high and the power consumption required for the MOSFET is very less. That is why this is so much important for the today's industry. And the JFET is a junction field effect transistor, where we will involve the theory of the PN junction just to achieve something, which we will discuss in detail in this class, because this class is strictly for the JFETs. So for the MOSFET, we will do separate class for the MOSFET. But here we are only discussing the JFET. So the junction field effect transistor. Junction field effect transistor, and in this particular device I will show you how the conduction can be dependent on the applied electric field and how that can be controlled. Because if you are having any particular semiconductor device, if the conduction is not controlled, that means that is a useless device for you, if you cannot control the conduction of any particular device. So firstly, how this JFET will look like and how the working principle will go on here. So we will start with the architecture of the device. if it is a rectangular blocks, which will be basically the cuboid, because firstly we will discuss with respect to 3D. So this is basically the architecture of this, and what will you do after this? After this, you will dope with some type of impurity in this. So I am saying that this is basically P-type substrate. That means this block is of the P-type. That means the majority charge carriers will be whole in this. And to achieve this, you will dope the any intrinsic semiconductor with the borons or any trivalent impurities, and you will get the P-type semiconductor. Then you will make the metallic contact in the upper body, upper surface, as well as in the lower surface. Then you will get one contact point here and one contact point here. And after this, you will dope with any other type of impurity. That means if it is this block, this duster is this block, what will you do? You will try to cover this entire portion, the cross section of this, with any other type of impurities. That means if you are having, are you able to see this ring? That means if it is your substrate, this entire body of this color pen is your entire body, and then you will, this ring of the blue color, like this you will dope with any other type of impurities. That means if it is a P-type semiconductor, you will dope this entire region. Only two sides you can see. That means this entire part you will dope with any other type of impurity. Okay, and this will become the basic architecture of this particular device, field effect transistor. I am not saying anything about the junction because the junction theory I will involve little bit later in this. But EDC is not that if I will apply this much amount of voltage, how much current I will get. If you are studying this, that means you are not studying the EDC. You are studying the analog electronics, that means the voltage current characteristic of the device. Here you want to see what is happening exactly inside the device. If that means in the diode, if you are getting this type of curve, if you are interested only in this VI characteristic or IV characteristic, that means you are only interested in the terminal behavior of the device. And that is the analog electronics, not the EDC. Because in the EDC, you have to tell the reason why you are getting this type of curve. Okay, what is the reason behind that? And whenever you will concentrate your study on that, that means you are studying the EDC. So I am not interested in this. So what will I do? If I want to see what is happening inside the device, I will draw the cross section here. Okay, and I will see how the charged particles are moving if I will apply any battery along any particular direction. So what will I do? I will cut this in between. That means if it is your device, I will cut from here with the cross section. That means along the cross sectional area I will cut this. Okay, and I will see how my device will look like. So if you will do that, you will get your device is something like this. I am only drawing the cross sectional area of this. Now this is the cross sectional device of this. That means if you will take a slice of this, and this will look like this. Because you have done the doping only in the surrounding. That means in outermost periphery, not inside the device. That is why in this side you will not get any doping of the opposite side, but this red is just the outermost cell. That means outermost periphery of the left side and right side. In between, if you will do the cross section, you will not see anything. That is why this part is missing. And in the books, you are getting directly this particular diagram. Because they are drawing only the cross-sectional diagram along the length. So, whatever the discussion I will do now, that will be purely of this particular thing, not of that. At the last, if you will try to calculate the resistance offered by the device, then you will take the length, width, the thickness and the width of the device. And that thing you can do by yourself. Because I am not interested in the terminal characteristic of the device. I am interested in what is happening inside the device. Okay, so I will eliminate this particular diagram from here now. And I want to see what is happening inside the device if I will apply any particular voltage from here. So this is my p-type, and we have doped with any other type of dopants, and this particular red color is connected from the back side of the device. That means how you have done the doping, you will do the doping in all the sides, and you have done the cross section. That means if you are seeing from this side, it will look like this. Front side will be something like this, and the back side will be connected with the red wire. Okay? So, if it is a p-type, you will dope with the N+. That means this red shaded area is nothing just the N+ type of device, and you will make the contact with this also. So, I am not saying any naming of the terminal, because the naming of the terminal will come with the characteristic of the terminal. Okay. Now what will happen if it is a p-type device, if you are providing the voltage from here to here. Why I am taking p-type device? Because you know the movement of the hole is in the direction of the applied electric field. Okay, and if the hole is moving along the electric field, the current will also move along the electric field. So no confusion of the direction you will get. Otherwise, in the electron, if the electron is moving along opposite side of the electric field, the current will be along the electric field. So little bit confusion you can get. That is why I am taking the p-type device. Now see, that means it is a p-type device, it is N+. That means one junction you have made here and one junction you have made here. And it is not your desire to make the junction. It will get maintained automatically. And later you will use these junctions as your applications. Okay, how these junctions can change the device characteristic. That means you are using this property. Okay, this junction will get maintained automatically by the device as you will provide the doping. So it is a P-N+ doping and it is a P-N+ diode. P-N+ diode, P-N+ diode. That means two diodes you will get here. That means in this particular field effect transistor, you are introducing the basics of the junction theory. That is why it is known as the junction field effect transistors. So now, if you will apply the battery along this particular device, in which direction the electric field will exist? Always the electric field will exist from higher potential to lower potential. That means electric field will go like this. And if the electric field is going like this, the hole will get the force in the same direction. Because what is the F? F is equals to E into E, where E is the charge on the hole. And you know the charge on the hole is positive, and electric field direction is downward. That is why the force on the electron in the hole is also downward, and if the hole is moving in the downward direction, you will get the current is also in the downward direction. Now see the terminal characteristics. This is the terminal which is providing the hole to the device. And what is the hole here? Majority charge carrier of this particular substrate. Yes or no? That is why the terminal which will provide the majority charge carrier to the device is known as source. And the terminal which will take out all the electron, all the majority charge carriers from the device, that is known as the drain. The terminal which will take out all the majority charge carrier from the device is known as the drain. And the terminal which will provide the majority charge carrier to the device is known as source. So this particular number will be known as VST. That means source to drain voltage. And this is known as the ID, drain current, or the more specified name is IST, the source to drain current. But what is the beauty of this particular device? If you will change the polarity of the applied voltage, in this case what will happen? The electric field direction will be upward. That means the hole will move now in the upward direction, and at that time this particular terminal will provide the majority charge carriers. So instead of drain, this terminal will become source, and this terminal will take out all the holes. That is why instead of source, this terminal will become drain. That means for this device, you cannot guarantee which terminal is source and which terminal is drain until application of the battery. Okay, that means the battery will decide which terminal will act as a source and which terminal will act as a drain. Okay, that means you have a freedom to interchange these two terminals. And whenever you are having such type of flexibility in any particular device, that is known as symmetrical device. Okay, so you got one information that the JFET is nothing just the symmetrical device because you are having the flexibility to interchange the source and drain. Now, come into the practical realization of this and see how the things are changing with respect to applied voltage. So, I am going in my previous thing. Now, if it is my VSD and I am taking this particular polarity and I am assuming that the current is going from source to drain in the downward direction. You know that electric field is in downward direction, that means the hole will move according to this line in the downward direction. Now if the VSD you are having, but instead of these variables I will take the numbers. If it is 5 volt and this terminal is grounded, that means this higher upper terminal is nothing at the higher potential of 5 volt with respect to 0 volt. So now first assumption I will take, and which is known as sharp degradation of the voltage from drain to source to drain. That means you will assume that the potential drop is not gradually happening. In the entire device the potential will be 5 volt. And if you will take this assumption, how the device will work, we will see this first. And we know that it is not possible. But I want to show you all the possibilities in the device, how many things can happen here. So you know that here N plus and P junction is there. That means whatever the depletion region you are getting, that will exist only in the low doped region, that means in the substrate. That is why I am not drawing any depletion region in the N plus side. Because you know that the doping is high, the depletion region will be less. So here the voltage is 5 volt and here the voltage is 0 volt. Here you are having the junction. That means always, now tell me one thing. Can you do this? Because all the time you are trying to achieve the current from source to drain or drain to source. Yes or no? But if this will happen, you will see there is a forward bias junction because this P type is at higher potential than the N type. That means you will get the forward biasing of this particular diode. And if it is happening means some current will go inside this particular junction. And you never want this type of characteristic in the device. So this polarity you cannot apply in this. Because whenever this is happening, you are doing the compromise with your device. Okay, but what will happen in this side? You know that this N plus is at higher potential than this ground. So this side it will become the reverse bias. So what I want to say, firstly I will assume that the voltage is constant throughout the device. So whatever the depletion region you are getting here, that will be the constant. What is my approximation? I am taking here, the voltage is not dropping here gradually. And if it is not happening, that means here the voltage is same, here the voltage is same, and here the voltage is same, except the boundaries. Here the 5 volt, here directly you will get 0 volt. And the rest of the device is having the same type of potential. And if the voltage difference is same across these two junctions, so depletion region will be constant. So you will get uniform depletion region. As you will keep on increasing this, you will get such type of device. And you will get the current in the downward direction. So this is the first case and this is the second case. That means and you know that VSD1 is less than VSD2. That means as you will keep on increasing the voltage from here, the depletion region of both the sides will keep on increasing and the available path available path for the hole to move from upper terminal to lower terminal is keep on decreasing. Okay, and if the area is decreasing means the current density will keep on increasing. Okay, and you are increasing the electric field, that is why the current will also increase up to some extent, up to which these two junctions, whatever you are making the depletion region, are not touching to each other. As they will touch, the available area for the conduction for the holes from upper body to lower body is becoming zero, and that time you will get the zero current from the device. And this is only the semiconductor devices. That means you are able to control the conductivity of this particular material. You can control the conduction offered by this particular device. That means you are able to achieve the controlled conduction in the device. Okay. Now, how it is looking like? In 2D, you are able to see the total width only. But if you will see in the 3D, like that, I am only drawing the top view. If it is your total area of the device, and you have seen that the depletion width is increasing in all the direction. Here I have mentioned only two direction because I have taken the cross section, but actual diagram will be something like this. Okay, that means if you will keep on increasing, this depletion width from here to here will keep on increasing. Previously it was this, now it will become like this. Further increment, this will become like this. And if you will increase for more higher value of this available width will be zero. Okay, that means no cross-sectional area is provided for the hole to move from here to here, and at that time you will get zero current from the device, and that value of the VSD is known as pinch off. Okay, this is known as the pinch off. Minimum value of the VSD for which the drain current will become zero is known as the pinch off for the VSD, under the assumption that the voltage is not gradually changing in the device. Then only this definition is valid. But you know the practicality that if here it is 5 and here it is 0, you cannot reduce the voltage sharply from 5 to 0. Definitely this voltage drop will occur gradually from here to here. Now we will see how that effect will come into the device, and that will rupture the entire thing whatever you have studied till now. That means this type of scenario will not happening there. So now I am taking the practicalities how the things is happening there, because this assumption is just to tell you the effect of the depletion region in the device. Now just to, if the voltage is gradually decreasing, so I can replace that like this. That is, it is 5, 4, 3, 2, 1 and 0. That means gradually it is decreasing the voltage. Now see, here 5 and 0 and here 0 and 0. Are you able to see or not? In which side it will becoming the more reverse biased. Here P and here 4, if I am taking at lower voltages, definitely it will be at, if I am taking at the middle, that means the voltage is 3. Because at this particular level, in each, throughout the device, the voltage will be 3. Now see here, 5 and 3. The reverse bias is, forward bias is of 2. 4 and 3. Forward bias of 1. 3 and 3. 0 bias. Now it is at higher potential, N plus is at higher potential than the P. That means here you will get the reverse bias. Here you will get more reverse bias, and at this terminal 3 and 0, that means the bottom side you will get the highest reverse bias. And you know, if the reverse bias voltage across the junction is continuously changing, the depletion width shape will also vary. Where the reverse bias voltage will be high, the depletion width will be high. Now, instead of the sharp such type of shapes, you will get modulation in the shape of the depletion width. That means here at this bottom surface toward the drain side, you are having more reverse bias. So you will take from here that the bottom side is having more reverse bias and the upper surface is having less reverse bias, like this. So instead of these dotted one, whatever you have assumed previously that throughout the device the voltage is same, then you will get these dotted one. But at this time you will get the wedge shaped. That means this depletion width is not throughout constant. So this is one side, and the same thing you will get for the second side also. And device will look like something like this. So I am just drawing a little bit correctly. Yeah, like this. And it is the symmetrical. If you are not able to see the symmetry, that means my drawing is not poor. If you are not able to see, that means my drawing is poor. But you have to assume that these two shapes are symmetrical in nature. Now see, if this is happening, that means the upper portion is not having that much wider depletion region, but the lower portion is. If you will further increase the voltage from here, what will happen? These depletion region will keep on increasing. Yes or no? So, I am taking that case where these depletion region will touch to each other. Now, this is a portion where you are getting the touching of these two depletion region across this, at least this point. But what will happen here? You know that the depletion region is having very high impedance. And if you are having such type of scenario, you are having three resistances. Here the value is 10 ohm. Here the value is 10 mega ohm. And here you are having 10 ohm and you are having the supply of 5 volts. Where you will have the most voltage drop across the highest resistive area. And in this side you are not having any low conductive resistance part. Low resistance part. That means these two areas are highly conductive part, but this particular region where you are getting the pinch off, that is the joining of both the depletion region, that is basically the insulated region. In the diode you have studied that in the depletion region the resistance is about to infinity. That is why the reverse bias junction is providing very high impedance. For little bit higher values, what you will get? This joining of these two depletion region will keep on increasing. Okay, previously you are having the voltage drop of 5 from upper body to lower body gradually, but as this function will happen there, joining of this, you will get very drop in the class, very high drop in the current. And instead of the gradual voltage drop, you will get all the voltage drop across this. The same thing will happen here. It is a more conductive region, it is also more conductive region, but it is an insulated region. That is why whenever you will get the open circuit in the device, you are getting the highest voltage across the open circuit terminals because the resistance offered by that particular region is highest. And in this time, here you are not having any particular channel. That channel means the path to flow the majority charge carrier from upper body to lower body. So at this time, this will touch to each other, and this phenomena of touching from where you are not getting the gradual decrement of the voltage throughout the device is known as the pinch off. And this will be the actual pinch off in the device. Because you have taken the practicality also, that means the current will not become zero now. Because something will also happen. Previously what happened, when you have taken that assumption that voltage is changing sharply from 5 to 0 and throughout the device is having the same type of potential, then the depletion region from here to here, entire channel will provide the highly resistive area, so you will not get any current. But what is happening here? Here you are having the channel in the upper portion, only the lower portion is sticking now. That means you are having the very high resistive area only in the lower side, towards the drain. Yes or no? Now see what is the lackness here, whatever we have missed in these sharp edges. What is the difference between the sharp edges and these wedge edges? What will happen now? You are having the voltage drop of 5 volt across this because it is the highest resistive area in the device. So 5 volt you are getting this. Now you are having two bodies like this. The first one is having 5 volt and the length is 5 micro. Now what is happening? The length is 1 micro and you are having the same voltage. Obviously the electric field will be high here. Yes or no? Because the separation of this 5 volt across this is very less. So electric field will be high here and that electric field will be sufficient enough to force these holes to penetrate this region and go towards this side. That means it will provide enough force. F is equals to E into E. Now the electric field in this region is very high. And if the electric field is very high, the force on the particle will be very high, due to which the kinetic energy on the electron or the majority charge carriers will be high, due to which that particular particle will penetrate this region. Okay? And if the particle is penetrating this particular region, that will offer some current instead of zero. So we have assumed in the sharp edges that the current will become zero, which is not practically. Practically the current will be there and that current will be constant because the electric field is constant now. And if the fixed number of charge carriers are moving from here to here because the doping you are not changing, that means the fixed number of charge carriers will move from here to here with the constant velocity under the influence of high electric field. Then the current will become constant. If the charge particle is not moving, velocity is not moving, that means the particle will become, now fixed number of particles will move along this and the current will become constant, and that region is known as the saturation region, where the current will become constant irrespective of your applied voltage, and that part is known as saturation. Now come, before saturation what will happen? As you will keep on changing this, the depletion region will keep on changing, due to which the cross-sectional area of the device will keep on changing, due to which you are able to control the resistance of the device. But after pinch off, the current offered by the device will become constant. That is, below pinch off, the device will act as voltage variable resistor, because as you will vary this, the cross-sectional area, that means the depletion region, can vary. Yes or no? And if you are able to vary these things, that means you are able to change the cross-sectional area of the device, due to which the resistance offered by the device will change. But after pinch off, the resistance you cannot change. Only the current will become constant, irrespective of the voltage. And whenever you are having this type of characteristic, where you are able to change the voltage but not the current, or in other words, if the current is getting maintained in the device irrespective of the voltage, that is act as a constant current source. So you can characterize this particular device below pinch off. The device will act as a VVR, voltage variable resistor, and from pinch off, the device will act as a constant current source. These are only the two regions, and it is from this to this. And I haven't applied anything across these two terminals. This entire device, whatever you are having, just because of this. So if I want to plot the ISD versus VSD, what happened here? In the initial case, if you will increase the voltage, the force on the hole will keep on increasing, due to which you will get higher value of the current, and that is what that is known as voltage variable resistor. So if you will increase that, the value will keep on increasing. At the pinch off and after the pinch off. From the pinch off means at the pinch off and after the pinch off, the current will become constant. Then only that device can act as a constant current source. So if it is increasing initially, and it will become constant. And this portion is known as triode region. And this portion is known as the saturation region. A lot lot of people are saying that it is a linear region. No, it is not the linear region. It can be linear only in this portion. It is not linear in this. See there, here the slope is changing. That means it is not a line. It can act as a linear component only in this particular region. That means in the deep triode. That means very deep into the triode region, and this is a linear region. Whenever you are saying that the MOSFET is acting as a linear device, that means you are dealing somewhere here. Not linear device, you are saying that it is a linear component. That means the VI characteristic is about to register. Then that particular device is acting somewhere here, not in this side. At this side it is just the triode region, which is basically the combination of line and parabola. All of you have studied the characteristic equation of, the IV characteristic equation of this. All of you have studied. So I am not interested on that much, on that. Because here I am here to teach you what is happening inside the device, not the equations. Now, do you have any problem in this? I don't think so that you will get any problem in this, because it is so simple. Because I want to see what is the role of these two yellow terminals. Sorry, those blue terminals. What will happen in this if you will apply some voltage here also? That means up to now you have studied only the effect of the vertical electric field. And you are getting the current because of the vertical electric field, and all the time you are assuming that you should not get any current because of the lateral electric field. Always your favorable current is from source to drain. So now I will eliminate the entire portion whatever we have studied here, and I will not apply anything here now, and I want to see what will happen here. So if I am first case, if I will apply like this and I am not applying anything from there, now what will happen? It is P and it is N, and if it is N is at lower potential than the ground, then what will happen? This particular junction will become forward bias, and you don't want this thing at any particular case that you should get the current from here to here. And whenever I am connecting here, it is also connected from the back side. So I will not provide any external voltage for this separately. If I am providing here, that means it is also connected from the back side. So you don't want any such type of case in the device. So you will never forward bias these two junctions, N plus P and N plus P. Always you will try to reverse bias this. So always I will apply the polarity something like this. Now I will see what is happening here. Now if I will apply some voltage here, what will it do? It will increase the depletion region of both the sides continuously and constant. Now for any particular VGS, now you will get the throughout same depletion region in both the sides, because here you are not changing the voltage gradually. Directly you are providing the voltage to this particular junction. So you can see here two type of electric fields are acting. The first electric field is lateral and the second electric field is vertical. And all the time you want the current from only vertical electric field. You don't want any current from this electric field. This electric field only can control this particular region. Okay? This available channel, because if you will increase this reverse bias voltage, the depletion region will increase. Yes or no? Due to which the available area for the conduction will keep on reducing. Okay, that means you are able to control the conduction from this terminal. And what is the terminal known as which can control that? That is known as the controlling terminal. Because it is not providing the current, but it can control the current. It will not be responsible for the conduction from here to here, but it can control the conduction from here to here. That means the controlling terminal, and more famous name of this is gate. Because what is a gate? Gate can control the number of person coming from outside to inside and the number of person going from inside to outside. That means it can control the characteristic of this particular device. This is known as the gate. Okay. Now I will apply both the things together. That means you are applying the VSD VSD as well as VGD. Now this is my device. That means from here to here you apply the reverse bias. Now what will happen? Something will happen because of this, and the excess depletion region you will get from here, which will be wedge in shape. So due to this you will get the continuous and the sharp edges. Now from this you will get something like this. Like this. Because this wedge shape is because of this, and this sharp black one is because of this. So in the device you will get the overall effect of this particular battery as well as this particular battery. That means the value of the current will be decided by this as well as by this. Okay. Now the value of the voltage for which the available width will become 0. That is known as the pinch off in the device. Yes or no? That is known as the pinch off in the device. If you are not providing the VGS is equals to 0, then you can have the maximum value of maximum width of the area. Yes or no? Because the area is depending on the width of the device. If the width is maximum, area will be maximum. And if the area is maximum, the current will be maximum. And that current is known as the IDSS. That means if you are not providing anything from this, that means if it is a ground, position, that means the current offered by this VSD will be maximum, because as you will provide this, it will increase the depletion region and the current value will keep on decreasing. Yes or no? That is why you have studied that just recently the plot. If VGD is equals to 0, then this value is IDSS, maximum value, and this value is known as the pinch off, VP. Now, if you will increase this particular VGD, what will happen? If this is 0, then available area will decrease and you will get the pinch off at lower values, because some of the depletion region will be decided by this and the sum of the depletion region will be decided by this. That means for lower value of the VSD, you will get the pinch off. So that case will be something like this. VGD is equals to 1 volt and it is a VSD. Okay, and the pinch off for this will be somewhere here and like this. And for the third case, VGD is equals to 2 and the pinch off will be something here. So as you will keep on increasing this, the pinch off voltage will keep on decreasing, as well as the device current will also keep on decreasing. This is ISD, that means the output current and output voltage. That is why this is known as output characteristic. Now I want to see how that thing is changing with respect to this current is changing with respect to this. That means ISD, VDG versus ISD. You know that if the value of the VGD is 0, means the current will be maximum, because entire area you are having and you have the VSD and this will be at constant VSD. You not have to think that you are applying only these two. You are studying the behavior of the current with respect to this under a certain voltage of the VSD. Because if the VSD is missing, you will not get any current. So, if at any particular VSD, VGD is 0, the current will be maximum, that is known as IDSS. And as you will increasing this VGD value, the depletion region in this side will keep on increasing, due to which the current will keep on decreasing, because the available width of this will keep on decreasing, due to which you will get the current towards 0 side. And you know that the current voltage relationship, because I am not interested in the derivation part here, so I am only providing the current and voltage relationship. The ID is equals to IDSS 1 minus VGD divided by VP to the whole square. Here I am only taking with respect to this particular device because I have provided drain at the lower potential. Now see here, what is happening? If you will provide something from here, if the VGD value is 0, you will get this portion is 0 and the current will be IDSS, which is maximum. If the VGD value is the VP, that means this value will become 0 and the current will become 0, and it is this. And it is a parabolic in nature because the current and voltage relationship is a parabola. And it's all about the working principle of the JFET.